Hi, welcome to today's lecture on asymmetric key cryptography, also known as public key cryptography. Now, asymmetric and public key cryptography is a technique that we're going to end up using to solve a lot of the problems that we've talked about so far that we've had with existing cryptographic solutions. So, asymmetric key crypto is going to give us a powerful tool for fixing a lot of issues that we've been dealing with. So, public key crypto allows you to encrypt with one key and have someone else decrypt the message with a different key. This is an important thing about public key crypto. There's two keys, and when you encrypt with one, you decrypt with the other. And this has two main uses. First is confidentiality. I can use this to send secret messages to someone. And the other is integrity. I can use this to ensure that something wasn't modified or to prove who created it. And those two are really very similar claims. So you may recall from the Intro to Modern Cryptography lecture that public key crypto is a cryptographic technique where both parties in the communication use different keys. So for example, in this case, Bob has a private and a public key that he's generated on his own, and his public key is public, it's known to the whole world, and his private key is private, it's known only to him. And if Alice wants to send Bob a message, she takes her secret message she wants to send him, and she encrypts it with his public key. That produces the ciphertext. She sends that to Bob, and Bob decrypts it with his private key to get back the original message. Now, this is very different from symmetric key crypto, where both people use the same key. In this case, they use different keys, one which is publicly known by the whole world, and one which is privately held by just one person. So public and private keys, how does this work? So the two keys are mathematically related, so that you can encrypt with one and decrypt with the other. And it's similar to the mathematics used in the Diffie-Hellman key exchange. In fact, some public key crypto systems are built on the same mathematics as the Diffie-Hellman key exchange, and others are built on similar mathematics. In a public and private key world, every user has two keys, a public key and a private key. The public key is not a secret, and anyone can have it. In fact, the more people that have it, the better. And a private key is a secret. Only the owner can have it. If the owner loses or somehow has their private key stolen from them, that's a major issue. So we have the two keys, public and private. So what sort of encryption can we do in an asymmetric system? Well, you can encrypt with the public key. So in this case, let's say that someone wanted to encrypt a message and they encrypt it with Alice's public key and they get a ciphertext. In that case, it needs to be decrypted with Alice's private key because the two keys are paired, the public and private key. So if you encrypt with a public key, you decrypt with the corresponding private key. The other thing you could do is you could encrypt with the private key. So if you encrypt a message with Alice's private key, it needs to be decrypted with Alice's public key. Now, these are the only two pairings that work. You encrypt with Alice's public key to decrypt with her private key, or you encrypt with her private key and decrypt with her public key. No other pairings work. So you can't encrypt with a private key and decrypt with the same private key, or encrypt with a public key and decrypt with the same public key. It doesn't work that way. These are the only two pairings that work for encryption and decryption. Okay, so if I want to use public key crypto for confidentiality, meaning to send a secret message, what do I do? Well, if Alice wants to send a secret message to Bob, then she computes the ciphertext by encrypting with Bob's public key the message. And she sends it to Bob. And Bob decrypts it by decrypting with his private key. That's fairly straightforward. If you want to send Bob a secret message, you encrypt it with his public key, and he will decrypt it with his private key. Okay, so who can perform the decryption of this message? Only Bob with his private key. No one else can decrypt the message because no one else has Bob's private key. Who can perform the encryption? Well, anyone, because Bob's public key is public, and that's the only thing you need in order to encrypt. So anyone can encrypt a message to send it to Bob, but only Bob can decrypt it. That sounds pretty good, actually. We just spent a whole lecture talking about how to securely exchange a symmetric key. When using public key cryptography like this, we wouldn't even need to, right? I mean, you could just encrypt the message with Bob's public key, send it to him, and he's the only one who can decrypt it. So in that case, I just went one direction, Alice sending a message to Bob. What if Bob wants to reply to Alice? Well, then he would encrypt the message with Alice's public key. He would just follow the exact same protocol, but in reverse. So If Alice wants to send a message to Bob, she encrypts it with Bob's public key. If Bob wants to send a message to Alice, he encrypts it with Alice's public key. Well, there's some problems with this. Problem number one is that public key cryptography is very slow. For example, for decryption, AES, which is a symmetric cipher, can encrypt at 100 megabytes per second, or faster actually, depending if there's hardware support and how fast the CPU is. On that same machine where AES is 100 megabytes per second, RSA is 1 megabyte per second. So it's 100 times slower. That's not good. So if you have a 200 megabyte file that you want to encrypt and send to somebody, you can encrypt it in AES in 2 seconds, or you can encrypt it in RSA in 200 seconds. So that's probably not good. So something like RSA, a public key system, is not good for large files. That would be actually absolutely horrible, actually, to try and send big files that are encrypted with a public key crypto system. How do we solve this? Well, we can combine symmetric and asymmetric tools and use both of their strengths. Symmetric key crypto is fast, but we don't really have good ways to share keys. And asymmetric crypto is slow, but allows us this great way to send a message to a specific person. So what do? Well, if Alice wants to send Bob a message and it's big, she chooses a random symmetric key, K. She computes the ciphertext where she does a symmetric encryption of that message. So maybe she uses AES or something like that. And she sends that ciphertext to Bob. Now, Bob can't decrypt it because he doesn't have the key. So she encrypts the key with Bob's public key. She sends that to Bob. The key is small, right? It's only 128 bits. The encrypted file might be huge. It might be multiple gigabytes. But the key she used to encrypt it with AES is small. So this public key crypto function will finish quickly because it's a small amount of data. And then she sends that to Bob as well. So Bob uses his private key to decrypt ciphertext 2. And from that, he gets the key K that was used to AES encrypt the message, and he uses that to decrypt the first ciphertext. So this uses the strength of both types of encryption to get the advantages of both. Most cryptography on the internet is based in part on this concept. So if you use SSL or HTTPS or something like that in your web browser, underneath it's performing symmetric key cryptography, which is fast to encrypt the data that you're transmitting, but it used asymmetric cryptography to transmit and choose the key. Okay, there's another problem with this. In order to understand this problem, we're going to have to add yet another character to our cryptographic games. And this character is going to be Mallory. Mallory is a malicious attacker who can intercept and modify messages. So from the last lecture, we talked about Eve, who was an eavesdropper who just looked at messages. Eve was a passive attacker. Mallory is an active attacker. Mallory intercepts and modifies. Okay, so if Mallory's there, what does our protocol look like? Okay, so Alice does what she did before. She encrypts her message with Bob's public key, and she sends it to Bob. Well, on its way to Bob, Mallory intercepts it and throws it away. Nope, too bad, Alice. Your message is never getting to Bob. Instead, she takes an evil message, she encrypts that with Bob's public key, and she sends that to Bob instead. Bob happily decrypts the message, and he can't tell that it's from Alice because there's nothing about the message that says who it's from that can't be forged. So Mallory, in this case, is able to send a message to Bob because anyone can send a message to Bob. And Bob can't tell that Mallory threw away Alice's message and replaced it with a different one. So this happens because the current technique I just described provides confidentiality for the data. When you encrypt it with someone's public key and send it to them, it's confidential. Because in this case, Mallory couldn't read the message from Alice. So even though Mallory intercepted it, Mallory can't read it because she doesn't have Bob's private key. And only Bob's private key can decrypt that message. So she can't read it, but she can throw it away, so she throws it away. And she can replace the message because anyone can send a message and encrypt it properly to Bob because Bob's public key is, well, public. So this means that we provide confidentiality. The message was never read by Mallory, but we don't provide integrity. Bob has no way to know that the message he received was a replaced version of what Alice actually sent. So what's our solution to this? Well, how can we use public key cryptography to verify integrity? That's the next answer. So maybe Alice wants to send a message to Bob that proves it was from her. For the moment, we're not going to consider confidentiality at all. The message is not a secret, but the important thing is that Alice wants Bob to know for certain that it came from her and that it wasn't replaced by anybody else. So she's going to compute an encryption with her private key of the message, and we'll call it DS. She's going to send that to Bob. Bob is going to decrypt it by decrypting with Alice's public key, and he's going to get the original message. So who can perform the encryption here? Well, only Alice, because it involves her private key. She's the only person on the planet who can produce DS. But who can decrypt? Anyone, because Alice's public key is public. That's why I say there's no confidentiality here. Alice sent this message that only she can encrypt, but anyone can decrypt it. Bob, Mallory, anybody. But the important thing here is that only Alice could have produced it. So when Bob decrypts the message using Alice's public key, he knows the message is from Alice because only Alice could have made it. That message can only exist if someone used Alice's private key to create it. So that implies that Alice was the one who created the message. Like I said, this does not guarantee confidentiality. And we call this a digital signature because we're not providing confidentiality of any sort, but really Alice is simply signing the message to prove it's from her. She's simply saying, this letter's from me, and she adds her digital signature using her private key. Now, I mentioned before there was a speed problem when we used public key cryptography for confidentiality. Do we have the same problem when we use it for integrity? What if you want to sign a really large file? Yes, we have the same problem. So it would be way too slow to sign a large file because public key cryptography is slow. Instead, what we do is we sign a hash of the file. So you hash the very large file, say using SHA-1, that gets you a 160-bit hash, and you sign the hash, and then you send all of that to the other party. So if I sign a hash of the file, what I'll do is I'll send the other person the original file and my signed hash. And they can verify it because they can decrypt the signed hash and make sure that that hash matches a hash that they calculate of the original message. So let's look now at an actual real-world public key cryptography system, and it's called RSA. This was actually the first public key crypto system. It was invented by Rivest, Shamir, and Adelman, and any bit size is actually okay. So remember with AES or other symmetric key ciphers, your bits, you only had certain choices for block size and for key size and things like that. In RSA, any size is okay. When it was released, 512 bits was standard, but now 2048 or 4096 bits is standard. It's just that computers have gotten faster, and so people feel like you need a larger bit size. Now you'll notice that these are significantly larger bit sizes than we saw when we were looking at symmetric key crypto. I'll address that at the end of this lecture. So the security of RSA is based on prime numbers and factoring, similar mathematics to what we looked at with Diffie-Hellman. In RSA, the public key is the product of two prime numbers. And the private key is those two prime numbers. And then the actual way you perform the encryption and the decryption involves using those two prime numbers. So we're not going to go into the details of the encryption methodology for RSA. I went into some details on Diffie-Hellman just to give you some mathematics. But for RSA, we're not going to do those details. Okay, so how secure is RSA? What's its security based on? Well, if factoring large numbers is easy, then RSA is easy to break. If factoring large numbers is hard, then RSA is hard to break. Because remember, the public key for RSA is a large number that's the product of two primes. The private key is those two primes. So an attacker wants to learn the private key would need to be able to factor the public key to get those two prime numbers. So if you can factor large numbers easily, then you can break RSA. But right now, we have strong reasons to believe that factoring large numbers is hard. But we can't prove it. There's no mathematical proof demonstrating that factoring large numbers is actually computationally hard. We strongly suspect it. There's lots of reasons to think it might be true, but we don't have a formal mathematical proof. Which means that if tomorrow somebody announces that they found an easy way to factor large numbers, modern cryptography is in a lot of trouble. So in this case, when you're breaking RSA, if you're trying to brute force RSA, you're basically trying to factor the public key into two prime numbers, which is hard and slow. Okay, so now here's a note on bit size. In symmetric key crypto, the key size is given in bits. So if I say AES 128, what that usually means is I'm going to use AES with a 128-bit key. And as we've already talked about in class, 128 bits measures the key space, which is the number of possible keys. If there's a 128-bit key for AES, then there are 2 to the 128 possible keys. In the RSA, for example, for an asymmetric key crypto, the prime number size is what's given in bits. RSA 2048 means RSA is using 2048-bit prime numbers to create public and private keys. It has nothing to do with the key space. So there's really no way to give good comparisons between symmetric and asymmetric security, just based on key size. You can't do it. The key size numbers are measuring totally different things. So it's not a useful comparison. But sometimes you'll find shady companies that try to sell you things claiming it's more secure because it uses RSA with 4096 bits, and that's better than your AES with 128 bits. Well, that's nonsense because you can't actually directly compare them. It's two totally different measurements. So summing up, public key crypto involves two keys that are mathematically related, and when you encrypt with one key, you need to decrypt with the other. And when using them, you need to be careful to make sure you know whether you are providing confidentiality, integrity, or both. I want to point out that in this lecture, I showed you how to use public key cryptography for confidentiality, and I showed you how to use it for integrity, but I didn't show you how to use it in a way that would guarantee both at the same time. So it'd be something good to think about. How can I use this to provide both confidentiality and integrity at the same time? Thanks. That's all for now.